now. So now let's move to compounds. What's a pure compound? Now we defined a compound as, how did we say a compound was defined? Two or more elements. That's right, 2 or more elements. Okay, so let's put that up here. 2 or more elements. Compounds are 2 more elements. Now the other thing about a compound, it doesn't vary. What is a compound? For example, let's think of one, water. What is water made up of? Hydrogen and oxygen. What's the formula? H2O. Okay, so H2O. That composition does not vary. Whenever we're talking about water, it is H2O. Water from the ocean, H2O. Water from the rain, H2O. It's always this way. Okay, and we call that the law of definite proportions, or law of constant composition. Okay, so those are 2 things. Definite proportion, law of definite proportions, or we say the law of constant composition. Okay, it's always H2O. And if you were to talk about percentages, we would say this is 89% about of oxygen and about 11% of hydrogen. That's a definite composition. It's always going to be that. It's never going to be 50% hydrogen, 50% oxygen. That's not water. Okay, so it's always going to be that. That's what we say, 89% oxygen, 11% hydrogen, and its composition does not vary no matter where you get the water from. It's still water, and that's the compound. Okay, now this hydrogen and oxygen are chemically bonded together. You can't really easily separate them. If to separate them, we're going to have another chemical reaction. They're not easily separated. They're chemically bonded. Hydrogen is bonded to the oxygen. Okay, that's another part of compounds. And they do not retain the identity of the components. So let's look at another compound, NaCl. Okay, you guys know what NaCl is, right? Yeah, that's table salt, isn't it? Okay, so let's write a reaction for that to see how we would chemically combine that. So we talk about Na, that's sodium, plus chlorine, that's Cl2, that gives us NaCl, that's our table salt, so let's balance it there. Okay, sodium, this is a soft metal, silvery, reacts with water. Would not want to ingest that. Okay, not good. This one, chlorine, is a toxic gas. Don't breathe that. That's bad for you. Okay, so these have some very distinct properties, dangerous properties for you. But what about table salt? Can you ingest this one? Yes. So that's the thing about a compound. It has its own unique set of properties, its own identity, its own unique set of properties, which is different from those components. Okay, so that's another thing about compounds. All right, so does that make sense about compounds? Because we want to compare and contrast that to mixtures. All right, so let's talk about mixtures then, as opposed to a compound. Okay, mixtures. What can a mixture be made up of? A compound has to be made up of 2 or more elements. What can a mixture be made up of? Well, think of some mixtures. You know what mixtures are, right? Give me some examples. A salad. What else? Yes, coffee, tea, Coke. All of those things are mixtures. Okay, how about if I put sugar in water? Is that going to be a mixture? Yes. Okay, so mixtures can be made up of what? Well, they can be made up of lots of things. They can be made up of elements, or compounds. Exactly. You might have a mixture of all elements. You might have a mixture of all compounds, or you might have a mixture of compounds and elements. It doesn't matter. It can be made up of anything, but not so with a compound. Okay, and then the other thing is that we said, oh, compounds don't vary. You know, it's that same composition all the time. Well, if you're going to make a salad, well, does it have to be a certain thing all the time? No, you can put lots of things, right? Okay, so it doesn't have to be. These compounds cannot vary. We've talked about definite proportions and constant composition. Salad can be made of lots of things. How about that little bit of sugar in water? Do I have to have a certain percentage of sugar in water, or can I add a little bit more? A little bit more, maybe take it a little bit less, right? Okay, so there is no definite proportion, is there? Okay, so that's the other thing. There's no definite proportion. It does vary by composition. Okay, and we said it's chemically combined. It's difficult to separate a compound. It's hard to separate hydrogen from oxygen. But if you have a salad, how hard is it to separate the lettuce from the carrots? Not very, is it? How would you separate the sugar from the water? How would you do that? You heat the water and what? Evaporate the water? Yeah, well, you're going to do something like that in lab. You're going to separate salt from water. And that's easy. You just evaporate off the water. And there, what do you have left behind? The salt. So you can separate them physically. So these are chemically combined. These are physically combined. Very easy to separate these. You can evaporate things. You can boil things. You can distill. Those are all techniques to physically separate components of a mixture. One of your first experiments is going to be you have this mixture and you got to separate the components. That's easy. You don't need a reaction, physically separating them. Okay, and it says, we said, oh, a compound does not retain the identity of the components. Well, what about sugar water? And after you evaporate off the water, what do you have left? Sugar. Wasn't it sugar before? Is this sugar after? Still retains its identities. Okay, so this one, it does retain, it retains the identity of the components. Retains the identity of your components. Okay, so does everybody understand the difference between mixtures and compounds? Okay. All right, well, there's two kinds of mixtures. There's heterogeneous and homogeneous mixtures. Heterogeneous and homogeneous. What does homogeneous mean? Does anybody know? Homogeneous mixture, what is that? Same, uniform? Okay, uniform. Well, we give that a term, and we call that a solution. So when I'm saying the word solution, I'm meaning homogeneous mixture. Like you put that sugar in the water and you stir it up. You have sugar water, right? It's uniform all the way through, isn't it? One spoon of sugar water is just like the next spoon of sugar water. It's uniform, same. Okay, well, what's an example of a heterogeneous mixture where one is not the same as another? Okay, sand and water can make different. Like how is different? What's another example? Sand on the bottom? Okay, what else? Give me other examples of different heterogeneous mixtures. Oil and water. Our salad example. Yeah, is that uniform all the way through? No, one bite might have the carrot, another bite might have the green pepper, another one might have... Okay, it's not uniform. Okay, so that's a heterogeneous mixture. All right, so those are the different types of mixtures, homogeneous and heterogeneous. Okay, what about granite? Let's do rock. Granite.
Wouldn't that be homogeneous?
Oh, is it?
One solid.
Does it look exactly the same? No, it's a solid, true. But if you look at it, does it look at, or marble? Aren't you going to have light spots and dark spots? So it's not uniform. It would be, because I would look at this section like, hey, there's dark spots. Oh, this section, oh, there's light spots. Okay, so that's an example of a heterogeneous mixture. And I know we're thinking mixtures. You're like, wait, shouldn't we always have water? No, we can make a solution of lots of things. You can have a solid solution, just made of solids. You can have a solution of air. Air is a solution. It's a mixture. It's a homogeneous mixture of gases. So air is what we call a solution. You don't have to have water when we're talking about solutions. I know oftentimes we think of that, but it's not. We can have solid solutions, liquid solutions, gaseous solutions. All right, make sense? Okay, so let's just test ourselves then and see if you can tell me which one of these is which. Okay, we're going to talk about element, we're going to talk about compound, or we're going to talk about a mixture. So which is which? Element, compound, or mixture? Okay, colors represent elements, little balls represent atoms. So let's take the first one. Is this an element, a compound, or a mixture? Element. It's an element because?
It's all the same matter.
It's all those same balls, right? Same color. Okay, now what is this one? Element, compound, or mixture? Element, compound? Element? It's the same atom? But there's two of them. Does you think it's a compound? Oh, but wait, what's our definition of a compound? Two or more elements. So, yeah, it's one element. So can this be a compound? No, but there are two of them. So what does that mean? You think, oh, gosh. Okay, well, what we're going to call this, we're going to call two of these balls together, we're going to call that a molecule. You heard that term before? Okay, so that's going to be a molecule. And this is an element. It's not a compound. Why is it not a compound? It's the same element, because we said a compound has to have two or more elements. We didn't say anything about atoms. We said two or more elements. If you have two or more atoms, you are called a molecule. So this is a molecule of an element. That's an atom of an element. Does everybody see the difference? Okay, so this is an element. These are molecules. Now what's this one? Compound. Why do you say it's a compound? Two or more elements. Are they the same composition? Yes, they are. Okay, now are these molecules? Yes, they are. Molecules of a compound, molecules of an element, atoms of an element. And then what's this last one? Mixture. Okay, obviously. Good. All right, very good. Yay! So now have we classified matter? We've classified matter by which way? Two ways so far have we talked about? Classified it by states and composition, right? Okay, so that's the two ways, by state and by composition. So you can classify matter in two ways now, can't you? All right, let's talk about a third way. Let's talk about properties. Okay, so let's talk about the properties of matter. We got physical properties, chemical properties, intensive properties, and extensive properties. Physical properties. What are physical properties?
How it feels, if it's shiny.
Okay, how it feels. Things that you observe about it without changing its identity. Ooh, I'm liking this PowerPoint. It's awesome. Okay, so physical properties then are things you can do and observe that don't change it into a different substance. Okay, so what are we talking about? Well, color, that's not going to change anything. What's the color of silver as opposed to the color of gold, right? You guys know that. Okay, color, hardness. Some things are harder than others. Sodium is softer, lithium is softer, gold is pretty hard. Okay, what about boiling point? Yeah, that's physical, isn't it? Sure it is. I can boil water, I can freeze water, but guess what it is? Water. It hasn't changed into anything else yet. Still water. I can freeze it, I can boil it, it's still water. So freezing point, boiling point, those are all the things that we can observe. Color, odor, all the things that we can observe without changing it into something else. Those are physical properties. So let's go back to what we were talking about, the states of matter. We freeze something, solidify something, liquefy something, turn something into vapor. You know what? Those are all changes of state, and they are all physical changes. So then, are we saying any change of state is a physical change? Yes, it is. Any state is a physical change. Okay, so what about chemical properties? Well, that makes something new. If you put a nail, water and oxygen, toss a nail outside, iron nail, what's going to happen to it? It's going to rust. Well, did it produce something new? Yes, it's that powdery stuff, right? Okay, well, does gold do the same thing? No. Okay, so that is a chemical property of iron, but not a chemical property of gold. So chemical properties are the way it reacts. Okay, it makes something new. You've changed to something new that wasn't there before. A new substance has occurred. Like rust, it's different, it's new. Gold won't do that. Those are chemical properties. Okay, then there's intensive and extensive. Intensive, what does that mean? Intensive, think of it as independent. Independent of what? Independent of the amount that you have. Okay, so intensive is independent of the amount that you have. Well, what would be an example of that? How about boiling point? You guys know what water boils at Celsius? What is it? At 100 degrees? Yeah, does everybody know that? 1 atmosphere boils at 100 degrees. Okay, so let's say I have a little tiny beaker of water, and I take its boiling point at 1 atmosphere. It's going to be, what? 100 degrees Celsius. Okay, what if I had a gigantic beaker of water and it's boiling? What's its temperature, boiling point? Same, it's 100 degrees. So did the boiling point change? No, no matter how much water we had, guess what? That is the boiling point. So that's an example of intensive. Doesn't matter how much you have. that property is still the same. Okay, boiling point is like that. Freezing point is like that. Color is like that. Those are all intensive properties. What about extensive? Well, that's the opposite. It matters how much you have. Mass, weight matters how much you have. Enthalpy, when we talk about enthalpy, that's an example, another example of the extensive property. It matters how much you have. All right, so does that make sense? Everybody got the idea between physical, chemical, intensive, and extensive properties? Okay, so let's see if we can decide the difference between chemical and physical properties. So we're going to stand up, and this time we're going to, if it's a chemical property, we're going to stand up and we're going to move to the back of the room. If you think it's a physical property, you're going to move to the front of the room. Okay, so the front of the room would be physical, and the back of the room is chemical. So we're going to put physical up here. Okay, so we're going to stand up and we're going to move up and down the aisles. And if you're not sure which way to go, talk to your neighbor. So let's all stand up. We've been sitting for a bit, so let's stand up. All right, so I'm going to call these out to you, and I want you to talk about it if you're not sure which way to go. All right, so melting of sodium chloride. Okay, so you got to move forward or back. Which way do you think? Physical is forward, chemical is back. Melting of sodium chloride. So we're not sure, we're sort of sure. Okay, so we're thinking, oh, it's like everybody's starting to move forward. Like, I'm not sure, she's going to hold her ground. Okay, so what do you guys think? Why did you move forward? Is melting one of the changes of state? Yes, it is. So is that a physical property? Yes. Okay, good. How about crushing up of rock salt? That's physical? Okay. Burning of sulfur. Okay, you think it's moving? All right, see what you think. If you're not sure, check with your neighbor. Burning of sulfur. Talk to somebody. Burning of sulfur. When we burn something, do we change it to something else? Yeah, you do. So it would be chemical then, right? Okay. Just like burning wood. What happens when you burn wood? The ashes. Is that something new? Yeah, we don't get the wood back, do we? Okay, so something new has occurred. So yes, burning of sulfur would be an example of that. How about rusting of iron? Chemical? Okay. How about dissolving salt in water? Is it physical? See if you can talk about it. Talk about it. What do you think? Is everybody deciding it's physical? Why is it physical? Why is dissolving salt in water physical? Because we can get it back? I didn't make gold with it? No. Darn. Okay. All right, we can get that back, can't we? All right, very good. Evaporation of alcohol. Chemical or physical? Evaporation. Evaporation of alcohol. Evaporation, that would be one of the physical states, right? Changing a state? Okay, so that is physical. Does everybody see that? Evaporation of alcohol, that's a physical. That's one of the changes of state. Chlorine gas becoming a liquid. That's another physical change, right? It was a gas, and now it's becoming a liquid. It's still chlorine. Very good. It's still chlorine. It just became a liquid, right? So that's a physical. Does everybody make sense? Yes. Are you getting that? Does that make sense? Okay. Digesting a candy bar. You guys are all moving to the chemical side? Why is it chemical? Do we get something back, something different? Right, is something new is produced, right? Yeah. Yeah, we're not getting that back. Okay. Something new is definitely produced. Okay. Seashells fizz when dropped in vinegar. It's chemical. Why? It's changing? What I said fizzing. What does that mean, fizzing? Producing a gas. Yeah, do seashells, they're not made of gas. Okay, so fizzing means a gas is being generated. So yes, that is a chemical change. You drop a seashell in vinegar and it will produce a gas. That's something new. That's something new there. Okay, how about iodine crystals are easily vaporized to give purple vapor? Are we moving? Are we moving? Iodine crystals are easily vaporized to give purple vapor. So vaporize, is that one of those what? Physical. That's one of the changes of state, isn't it? Now, I said purple vapor, and you're probably like, well, does that mean it's a change to something else? Well, iodine crystals are very, very deep purple, by the way. So the key word there would have been what? Vaporized. Okay, does everybody get the idea between chemical and physical? Does that make sense? Okay, awesome. You guys did a great job. Good job. All right, very good. Okay, well, we've talked about different ways that we can classify matter, didn't we? We can classify matter by what? What did we say? State, composition, and okay, and the properties, didn't we? Those are the three ways that we classified matter. Now, another thing we're going to do with matter is we need to measure it. Okay, so we need to measure things. So we're going to talk about measurements. All right, so let's say I have this object, and I measured it, and it was 24. There you're like, well, what? 24 what? Okay, so whenever we talk about measurements, I have to have something else besides the number. Okay, so 24, like what? 24 yards, 24 miles, 24 centimeters, makes a big difference. So whenever we have a number or a measurement, we include always the number and the units. These are the units. It's very, very important to include the units with the number. They go together. You cannot have the number without the units. Okay, that's going to be very important. We're going to multiply and divide numbers, but we're going to also multiply and divide units. So we need them both in a measurement. How important are units? Very, very important. This is Mars Orbiter. Mars Orbiter, you can ask NASA about that. Did you guys heard about that? Yep, they burned up the Mars Climate Orbiter. What happened? Somebody forgot to put the units. That's what happened. There were two teams working on the Mars mission, and they were using different sets of units. The NASA scientists in Pasadena, California, were getting thrust data from Lockheed Martin in Denver. Okay, well, they assumed that the thrust data were going to be in metric, but in reality, they were English. But the Denver people did not put the units with it. So when NASA got in California, they assumed they were metric because there were no units. And so this is thrust data, right? So they built this $125 million Mars orbiter. They go through all the trouble to build it. Then they go to the trouble to launch it. Then it travels all the way through space. Finally gets to Mars, and the thrusters is what keeps it from up and down in the atmosphere. So it gets too far down in the atmosphere, and the whole thing burns up. So, wow. How important were those units? Woo, very, very important. So, yeah, somebody's in trouble. All right, so in here, we're going to always include the units, aren't we? Yes, we have to include the units. It's going to be very, very important. All right, well, let's talk about the numbers first, and then we'll talk about the units. Let's talk about the numbers. Now, there's two kinds of numbers. There's an exact number and a measured number. Okay, so let's practice with the exact number. Counted numbers is an exact number. So how many people are in this row? 4. Do we all agree? Does everybody say 4? Is there 4.2? No. 3.5? No. Okay. Okay, so we all say there's 4 people sitting here. That's an exact counted number. We all agree on that. That is exactly 4. It is 4. 1, 2, 3, 4. Okay, that's an exact counted number. The other number we want to talk about is a measured number. Okay, measured number is where we take a measuring device and we measure the number. So here is a ruler, and we're going to measure that number. Okay, now we see marks. Does everybody see where the marks are? Every centimeter has a mark. Okay, so we got the marks. Okay, so if we were to measure that black line, what do we think we have? I heard 4.6. I heard 4.5. I heard 4.4. Oh, so now we got all different numbers? Okay, we all were for sure agreed it was exactly 4 people. How come we're all like, it's a little different now? What's the problem? We're measuring in what? What are you doing? Everybody got the 4 right, so I heard 4.5, 4.6, 4.4. So we all got the 4 agreed on, but where are we differing then? It always includes an estimation number, doesn't it? So you see how we were estimating that digit? Okay, that's an estimated digit. So whenever you are taking your measurements in lab, anywhere, you're going to include every mark that you see, like the 4 mark. You're going to include the marks, and you have to do one estimated digit. The estimated digit is between marks. So you're going to estimate something between marks. So whenever we're talking about measurements, you take the marks and then one estimated digit between marks. Okay, so let's go again. All right, how about this one? What do we have here? Anybody else? 4.5, 7? Yeah. Yeah, it could be 4.58, maybe. Okay, all right, so what's going on with this one? Do we all agree on the 4? Yeah, is that because it's a mark? How about the 5? Do we all agree on that one? Why are we agreeing on that one? The mark? Okay, but what about this last digit? Okay, that's where we're estimating, isn't it? Okay, this is the estimated digit. It's between the last mark. So whenever you're taking a measurement, remember you get all the marks plus only one estimated digit. And the very last digit is the estimated digit. So the 2 differences, the 2 measurements are exactly the same. Which one gives us a better understanding of its true length? Yeah, the second one. Why? Has more marks, right? Okay, well that's important because if you look at these numbers, remember, the last digit is the estimated measured digit. So if this is estimated, it kind of tells you how accurate it's going to be, isn't it? You're like, okay, that was not so accurate. But if this is the last estimated digit, then you're like, oh, these are marks. So you see how this helps us get a better true value, the idea? Okay, well, let's do one more. All right, now what about this one? Okay, so would we call it 3? Because if I just call it 3, I think this is the estimated digit. Okay, so we do have to say 3.0 because you do want to include an estimated digit. So we're saying, hey, it's right on the 3 mark, so it's 3.0. So that 0 is important. Okay, so when we're doing these measurements, we can't drop off zeros and we have to be very careful. So then we have to talk about accuracy and precision because we can talk about accuracy by how true it is. So that's the next thing we want to talk about is accuracy and precision. All right, so let's talk about accuracy and precision. I think the easiest way to do that is to talk about accuracy and precision in terms of our bullseye here. So we're going to define accuracy as how close we are to the true value. Okay, how close we are to the true value. All right, we can see this one was more accurate. It helps us get to the true value. So we're going to call the bullseye the true value. That's going to be accuracy. Now, what's precision? Precision is how close your answers are together, how reproducible it is. May or may not be accurate, but how reproducible it is. Okay, so who's good with darts or not good with darts that would like to throw some darts? And we'll talk about accuracy and precision. All right, come on up. Tell everyone your name again. Okay. And you can stand as close or as far away from that dartboard as you want. Wherever you want to stand. And just throw it at the dartboard. Okay, good. Just throw it all around, however you want to do it. It's okay. All right, that's a great one. All right, awesome. Okay, so let's talk about accuracy and precision. Accuracy is how close we are to the true value. So how's our accuracy? Not so much. Precision is how consistent and reproducible we are, or do we have a lot of variety? A lot of variety. Does that make sense? A lot of variety. Okay, so we'd say this is an example of something that's not precise, nor is it accurate. Okay, let's go again. Who else would like to try? All right, come on up. Stand next to it. Sure, you can stand next to it if you want to. As close as you want to get. There you go. All right. Okay, that's pretty good. That's pretty good. Awesome. Let's say you did it right there. Okay? All right, now what can you tell me about accuracy? Not so accurate, but what can we say about precision? Very precise. Do you see that? So this is the difference between accuracy and precision. So what if I had it like this? Accurate and precise. And if it was like this? Precise, but not accurate. Okay, so you don't have to have them both together. Like this is very precise, but not accurate. Okay, and if we had them like this? Got nothing. Okay, so does everybody understand the difference between accuracy and precision? Okay, now accuracy and precision is very important when we're talking about measured numbers. But accuracy and precision, wow, that's hard to talk about with counted numbers because it's pretty accurate and we're pretty precise. Because if I count them, 4. Let's do it again. 4. Wait, one more time. 4. I must be very precise. But I'm also very accurate. Do you see that what makes it accuracy and precision apply to are the measured numbers we're talking about, right? Measured numbers. Because the counted numbers are very accurate and very precise. We're talking about measured numbers. Now, we said this 0 was important. So we would say that 0 is significant. We can't just drop it off because it means something. Remember, we're taking measurements. It's all the marks plus one estimated digit between marks. Okay, so those digits become important. They say something to us about accuracy. So we have to count what's called significant figures. Okay, significant figures are what we are going to learn how to count, significant figures. Okay, now we're going to follow these rules for counting significant figures. Now, significant figures are not the same as decimals. Don't think they are. That's just going to confuse us. Significant figures are not the same as decimals. Okay? Now, significant figures, why do we have them? We're going to follow certain rules. And we have them because we need to pay attention to the calculations with significant figures. Because remember, we're thinking, oh yeah, measured numbers. Again, this applies to measured numbers. That estimated digit helps us understand accuracy. So we're going to count the significant figures to make sure we don't come up with an answer that's more accurate than we really used the instruments to help us measure. That's the purpose of the significant figures. Okay, so we're going to use significant figures in our calculations. All right, so let's talk about how do we define significant figures? Any digit is significant. That's easy. All numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. They're all significant. Okay, all digits are significant, 1 to 9. Now, it's the 0 that becomes questionable. Now, with the zeros, we have 3 conditions. Leading zeros, middle zeros, and end zeros. So let's talk about that. Leading zeros. Zeros leading. What does that mean? Leading. That means in the front. In the front of what? In the front of other numbers, right? Okay, so this is an example. 0.013. This is an example of leading zeros. Zeros are where? Where are they? They're in the front. In the front of what? In the front of digits. Okay, that's all I'm caring about. Digits. All right, so how many significant figures? Now, the leading zeros never are significant. So how many significant figures are in this number? 2. Because leading zeros are never significant. All right. Let's move the decimal over here. Now, How many significant figures do I have? Still 2. Because I still have leading zeros, and what did we say? Leading zeros are never significant. So those don't count. So I still have 2. All right, let's change it to this number where I put the decimal in front of the zeros. How many significant figures do I have? 4 or 2? Why do we say 2? Zeros in the front of a digit, what do we say? Never significant. So this number has how many significant figures? 2. Still 2. Do you see the difference? Now, has the decimal number been changing all over the place? Yeah, it has. But remember, a significant figure is not the same thing as a decimal. This has how many decimal places? 4 decimal places, but how many sig figs? 2. All right, let's put the decimal between the zeros. Now, how many decimal places? 3, but still how many significant figures? 2. Okay, let's move it back over here in front of the 1. How many decimal places? 2, and how many sig figs? 2, still 2. Do we see that? Okay, that's leading zeros. What about zeros in the middle? They're always going to count, like 302. That's in the middle of what? 2 digits. So this one always counts. So how many sig figures does this have? What if I have a decimal right there? Still 3, right? It's always 3. The 0 didn't change. It's still between the 2 digits. Okay, and then the very last one is end zeros. Now this one has an if. Yep, they will be significant if there's decimals. This has to be decimal somewhere. Okay, so let's take a look at this number. Okay, what kind of zeros do I have? Leading, middle, or end? End. So what do we say? End are significant if there's a decimal. Do I have a decimal somewhere? Yep. So that means these zeros are significant. So how many significant figures are there? 1, 2, 3, 4, 5. Does everybody see why there's 5? Okay, well, what if the decimal was over here? Still 5. That's right. Now, what if I don't have any decimal at all? Then it's only 3 sig figs. Okay, so the end zeros are only going to be significant if there's a decimal. If there's not a decimal, they're not significant. Does that make sense? Okay. All right, well, let's see if we can practice. How many sig figs is this one? 3. Good. 3. What kind of zero is that? Middle. And we said middle was what? Always significant. How about leading zeros? What are those? Never significant. End zeros? If there's a decimal. Okay, awesome. You guys got that. Very good. All right, let's go again. Okay, now how many significant? 4. Perfect. 3, because there is a decimal, right? So end zeros are significant, so there are 3. Perfect. 1. Why'd you say 1? No decimal. Awesome. 2, because leading zeros are never significant. Okay, now we can start mixing in some zeros here. I got leading zeros, I got end zeros. So the answer is 3. Perfect. Now we're really mixing them. Okay, so you have to think. That's right. Perfect. Oh, and that's it. Okay, so is everybody can count the significant figures? Okay, now another thing that we need to count with significant figures are scientific notation. You guys familiar with scientific and exponential notation? Okay, if we're not familiar with them, you might want to check your appendix in the back of your textbook. Okay, so a number like this, 4.3 times 10 to the third, that's a really big number, right? It would mean 4300. So I would be, say, 4.3, and then I'd go 1, 2, 3. So this number is 4300, 4,300. Okay, now, you know a negative, that's a positive exponent, means a big number. What about a negative exponent? What does that mean? It's a small number. It goes the other way. So I'd go 3 the other way, right? So it would be 0.0043. Okay. Now, the way we're going to do scientific notation is that we don't expand it out. Don't move the decimal anywhere. So if I'm looking at this number, how many sig figs do I have? 2, just 2. So when we were doing that number a minute ago, or let's say 52300, and these were not significant, well, how would I write that? Well, these 3 are significant. So to clarify that, I would use scientific notation. 10 to the what? 1, 2, 3, 4. Does everybody see it's 10 to the 4? Okay, that shows my 3 significant figures. So we can use scientific notation a lot. Scientific notation means there's 1 digit and a decimal. Now, we can have exponential notation, which can mean, for example, 52.3 times 10 to the 3. That's the same number, but notice that I have more than 1 digit here before the decimal. Okay, that happens sometimes, and we can do that in calculations. That's exponential notation. That's fine. But when you get down to your final answer in scientific notation, you do want 1 digit and then the decimal. Okay, so don't expand those out when we're doing that. All right, great. Well, we can count sig figs. Now how about doing calculations with them? Okay, woo, calculation rules. All right, so let's talk about how to calculate with our sig figs. Now, what did we say? Sig figs and calculations, and we're counting sig figs. These are rules apply to measured numbers or exact numbers. What are we talking? Measured numbers, right? Remember that, because there's something different going on with exact numbers. All right, let's do multiplying and dividing. If you are multiplying and dividing numbers, then your answer will have the least number of sig figs. Okay, so let's do an example of some of those calculations. For example, if I were multiplying these two numbers together, 6.221 times 5.2. Now let's count the sig figs. How many sig figs do I have here? 4. How many sig figs do I have here? 2. So what's the least number? 2. So my answer needs to have how many sig figs? 2. Okay, but when you put this in your calculator, you're going to get like 32.43492. I can't have that number because I'm like, whoa, that's a really accurate piece of number. But it's not, because I didn't have that much accuracy. So I have to reflect that. So the least number we said was 2. So how many sig figs can I have here? 2. All right, so here is 2. So what am I going to do? We're going to do what's called rounding. And if it's 5 and up, you know, to round 1. Okay, if it's less than that, so this would round to what number? 32. Does everybody see how that works? Okay, so multiplying and dividing, what's our answer got to be in? Least number of sig figs. Okay, multiplying and dividing, least number of sig figs. So you count the sig figs for each number, and whichever one had the smallest number of sig figs, that's what you're going to give your answer to. And you're going to round the answer to that. Okay. All right, well, let's do adding and subtracting. Now, with adding and subtracting, the rule is, adding and subtracting, your answer must have the least, okay, number, and this is where it differs, of decimals. And this is where we have the most trouble. Your answer is the least number. Now we do count decimals, but not sig figs. So don't mix that up. I think the biggest mistake we make is mixing these up. Okay, that's the most common error that's made. Okay, your answer must have the least number of decimals. So let's add some numbers together. For example, let's do this number, 0.71. And let's do 92.2, and we're going to add those together. So in our calculator, we would get 92.91. Now, how many decimals, since we're adding, how many decimals does this number have? 2 decimals. How many numbers does a 92.2 have? 1 decimal. Now be careful. We're counting decimals. How many sig figs does 92.2 have? 3 sig figs, but I'm not counting sig figs, am I? No, we're counting decimals. So if that has 2 decimals, that has 1 decimal, how many decimals should my answer have? 1, not 1 sig fig. 1 decimal. So I'm going to box this off, right? So it becomes, my answer is rounded to what? 92.9. Does that make sense? Okay. Now, when you're counting sig figs for an exact number, that's going to be a little bit different, because how can I represent the accuracy? How can I represent the accuracy of an exact number? So let's go back to where we were talking about our 4 people. So how would I represent the accuracy? Would I say 4.01? That wouldn't know. It'd have to be 4.00. Aren't there 4 people here? Okay, so what would the next digit be? Has to be a 0. Can't be a 9 or anything, can it? What's the next digit got to be? 0. And the next digit? 0. And the next one? 0. Ah! How many zeros do I have to have? Infinite. So if you're talking about exact counted number, that has an infinite number of sig figs and decimals. So that's why when we're counting numbers and we're trying to multiply things, you have to be careful, because if you're multiplying by an exact number, it has an infinite number of sig figs and decimals, so it's never going to be the least one. So in other words, we don't really pay attention to the exact counted numbers when we're counting sig fig calculations. Does that make sense? Okay. All right. So, well, that was pretty easy. Weren't those rules pretty easy, right? Those are easy. Well, you know, those are only one-step operations. You can do multi-step operations. Multi-step. Okay, so what happens when we do multi-step? You still follow the same rules. Okay, so let's put an example of a multi-step problem up here. Let's say 4.562 times 3.99870 divided by parentheses 452.6755 minus 452.33. Okay, whew, there's our problem. It's a multi-step problem. Now, we're going to have to pay attention to our rules. Same thing. Now, you guys know the order of operations? What's the order of operations? PEMDAS. PEMDAS, PEMDAS, that's parentheses, exponents, multiplication, addition, subtraction. All right, so we're going to do parentheses first, okay? Now, we still have to follow the same steps. I could put this all in my calculator at one time and get an answer, sure. But if I do it that way, I won't be able to keep track of the decimals and the sig figs in each of the subsequent steps. So you really have to step it out when we're talking about measured numbers and trying to figure out what it's going to be at the end. Now, you're going to round. You can only round one time. One. Why can't I round lots? Well, because you do one operation. Like, here's the true and accurate answer. I do one step, and I've rounded. Okay, I do another operation, and I've rounded. I do another operation, and I've rounded. Okay, what happens to my final answer? It's way off, and it's wrong. Master in chemistry says it's wrong. The answer's wrong on the test. It's like, wow. Why? I did all the steps right. It's because you rounded too much. How many times can you round? One. And you're going to round at the end. Okay, so let me just show you how to step this through. All right, so we're going to round one time, and we're going to round one time only at the end. So we're going to do the order of operations first, and that's in parentheses. So let me rewrite this. 4.562 times, I'm going to show you step by step, 3,99870. Divided by, and I subtract those two numbers, and in my calculator, I get 0.3455. All right, it's subtraction. So what's the rule supposed to be? The answer is in the least number of what? Decimals. Okay, let's count decimals. How many decimals in this number? Okay, 4. How many decimals in this number? 2. What's the least number? 2. So my answer better have 2. But can I round it right here to 2? No. It's like, oh, what am I going to do? I got to still keep track of that. So the way you're going to do that is you're going to draw a box around what it should be. And this is what it should be because we said 2 decimals. Okay, there's 2 decimals. So I'm going to draw a box around it. But when you type this into your calculator, Are you going to put a rounded number in right here? No, you're going to have to use what? 0.3455. You can't round. Remember, no rounding. Got to use the whole thing. But you still have to keep track of the rules. So this is what you're going to do. You're going to say, I'm going to use the whole number, but this is what it should be. So I'm going to box that off. Okay, now let's go to the next step. Multiplying and dividing. What's my answer supposed to be in? Least number of sig figs or decimals? Which one? Sig figs, because it's multiplying and dividing, right? Okay, let's count sig figs. How many sig figs here? 4. How many sig figs here? 6. How many, be careful, how many sig figs in the box? 2 in the box. If you count 4, you just ignored your first step. You just wasted all that time that you spent counting all the decimals and boxing it. Do you see why this is 2 sig figs and why it's not 4 sig figs? Even though you're using that number in the calculator, it is still boxed off to 2 sig figs. All right, so the least number of sig figs is what? 2. Okay, so let's put that in our calculator, and we would get 52.79904313. But how many sig figs am I supposed to have? 2. So what's my final answer going to round to? 53. That's it. No decimals, just 53. Okay, so you really need to step these out and box off your answers, be able to see what it would be. You could put this in your calculator, but your calculator is going to show you this, and you're going to be like, well, how many sig figs and decimals am I supposed to have? So you do need to step it out and box off your answers to be able to see what your final answer should be rounded to. And remember, how many times can you round? Once at the very end. Now be careful with your calculator, because your calculator will drop significant zeros. Like instead of saying 3.0, it'll just say 3. So be careful when you're using your calculator and pay attention. It adds significant digits, it drops them. So does that make sense? Okay, so what we're going to do is we're going to keep practicing a few more problems, and we'll do that on Thursday. So between now and Thursday would be a good time to practice those sig fig rules and calculations, because we're going to add to it on Thursday. All right? Okay, good job, everybody, for your first day. Woo! Good job, everyone. All right, so when are you going to study again? Yes, every day. Every day. Today and tomorrow, and we're going to be back on Thursday. All right, good job. We'll see you on Thursday.